Whitened clip as a likelihood surrogate of images and captions. CLIP is a very powerful vision language model that learns to align images and text into a shared embedding space. But despite its success in many downstream tasks, it lacks a clear probabilistic interpretation. Such a probabilistic interpretation can be useful for a lot of downstream applications. Language models explicitly approximate such an interpretation with a negative log likelihood training loss. Classical image analysis methods used to explicitly approximate such a function based on some prior knowledge. Deep learning methods that have advanced the image analysis field greatly in the past decade and a half only implicitly approximate a probabilistic function. We propose a direct likelihood approximation using CLIP. If each of the CLIP embeddings is a small vector x1, x2 of dimension d, and we have a large matrix X containing all of our CLIP embeddings, then we can compute the mean of these embeddings and the center embeddings. In addition, we can compute an empirical covariance matrix based on these samples. Using the covariance matrix, we can compute a whitening matrix W, which is not unique and can be computed in many ways. We use PCA to do it. The whitening transform, once W is obtained, is applied on the centered embeddings and not on the raw embeddings. So what are the advantages of using this whitened embedding space? It's purely data-driven. It's an invertible transform. We compute W once, and then we can use it in an inference time efficiently. And the whitened features have zero mean and unit variance. We now compare between the regular clip embedding space and the whitened clip embedding space. In the regular case, the covariance matrix is not diagonal, meaning that features inside the embeddings have relations between them. In the whitened case, the covariance matrix is diagonal, indicating no correlation. When we look at the different features on a big group of samples from MS-COCO validation set, we can see that each of the features has a different variance and different mean in the raw clip space. In the whitened space, all of the features have zero mean and unit variance. So they are identically distributed, approximately Gaussian, and so non-correlation indicates independency. If we have a group of IID standard normal distributed vectors, then this is their likelihood function, and this is their log likelihood. This is a very simple equation with a constant and the norm of the whitened embedding. So using CLIP and a whitened transform, we can get a very simple and direct log likelihood function for images and for captions. We now show a few use cases of this likelihood. First, we can see here real images and AI-generated images with artifacts like 6 fingers and a blue dog. We can see that the likelihood scores of the artifacted images are lower than the likelihood scores of real images. Another example, we can look at these captions, starting from this caption with many names in it. If we remove one name, like Minnie Mouse becomes a mouse, the norm goes down and the likelihood goes up. On the other direction, if we take a generic term like woman and change it into bride or Jenny, the norm goes up and the likelihood goes down. The more complex the text is, the less likely it is. Here we perform an experiment with ImageNet R where we have similar images in different styles and different domains. Similar domains to real images like graffiti are pretty similar distributed, but not realistic domains like sketch or video are very out of distribution, which means higher norms and lower likelihood scores. We also identified a bias in a generative model. We used the unclip framework, and when we took an image and generated another image using the exact embedding, and then tested the likelihood of the original embedding compared to the new embedding, we can see that the new images have lower likelihoods compared to the original images. In this work, we introduced whitened clip, an isotropic variation of the clip embedding space. This is the first direct likelihood approximation using the CLIP model. The likelihood approximation is sensitive to text complexity, artifacts and images, domain shifts, and it identifies generation model bias. Thank you.